the birth of a new era, Einstein's theory of relativity. In the early 1900s, physics was on the brink of a revolution. For centuries, Isaac Newton's laws of motion and gravity had stood as the pillars of understanding the physical world. Yet, as scientists explored deeper into the mysteries of light and electromagnetism, cracks began to appear in these foundations. It was against this backdrop that a young German-born patent clerk named Albert Einstein would change our understanding of the universe forever. The puzzle of light and motion. Einstein was working at the Swiss Patent Office in Bern when he began pondering a puzzling question. How do objects behave when moving at very high speeds, close to the speed of light? At the time, physicists believed that light, like sound, needed a medium to travel through, a mysterious luminiferous ether that supposedly filled all of space. Yet, experiments repeatedly failed to detect this ether, raising doubts about its existence. Einstein had a different idea. In 1905, he published a paper titled On the Electrodynamics of Moving Bodies, proposing a radical new theory, special relativity. He argued that the laws of physics should be the same for all observers, regardless of their motion, and that the speed of light is constant, no matter how fast the observer is moving. This simple idea had profound implications. It meant that time and space were not absolute as Newton had believed. Instead, they could stretch and contract depending on the observer's motion. Objects moving close to the speed of light would appear shorter, and time would slow down for them, a phenomenon called time dilation. These effects, while tiny at everyday speeds, become dramatic as objects approach the speed of light. Einstein's theory did something extraordinary. It reconciled the laws of motion with the rules governing electricity and magnetism, laid down by James Clerk Maxwell. It also suggested something revolutionary. There was no need for the ether at all. The universe was governed by a single, elegant framework. The famous equation, E equals mc squared. One of the most famous outcomes of Einstein's 1905 work was the now iconic equation, E equals mc squared. This simple equation revealed that energy E and mass m are interchangeable, connected by the speed of light squared, c squared. This meant that even a tiny amount of mass could be converted into a vast amount of energy, an insight that would eventually lead to the development of nuclear power and weapons. However, despite its groundbreaking nature, Einstein's work on special relativity was not universally accepted at first. Many physicists found it difficult to abandon their long-held beliefs in absolute space and time. Yet, one of the era's leading physicists, Max Planck, recognized its significance, helping to spread the ideas across the scientific community. Minkowski spacetime. In 1908, mathematician Hermann Minkowski gave a new perspective on Einstein's theory, showing that space and time were not separate entities, but part of a single four-dimensional continuum called spacetime. This geometric interpretation of special relativity added a new layer of understanding, one that Einstein himself would later embrace. The leap to general relativity. While special relativity was a triumph, it had one limitation. It only applied to objects moving at constant speeds. It couldn't explain how gravity worked. Einstein knew that to truly understand the universe, he needed a theory that could account for objects accelerating and being affected by gravity. This led Einstein to the next stage of his journey, general relativity. Over nearly a decade, between 1907 and 1915, he wrestled with the problem of gravity, eventually arriving at an astonishing conclusion. Gravity wasn't a force in the traditional sense. Instead, massive objects like stars and planets warped the fabric of spacetime itself, creating curves and bends. These distortions in spacetime would cause objects to move as if they were being pulled by a force, what we experience as gravity. One of Einstein's key insights came from what is now called the equivalence principle. Imagine standing in an elevator. If the cable snapped and you were in free fall, you wouldn't feel the effects of gravity, at least not until you hit the ground. Einstein realized that free fall was essentially the same as floating in empty space. There was no way to tell the difference. From this, he concluded that gravity and acceleration were two sides of the same coin. The first test, light and gravity. By 1911, Einstein's new theory was beginning to take shape. He predicted that light passing near a massive object, like the Sun, would be bent by the object's gravity. This was a bold claim, but it could be tested. During a solar eclipse, when the Sun is obscured and stars near its edge can be observed, scientists could measure the bending of starlight. In 1919, during a solar eclipse, British astronomer Arthur Eddington confirmed Einstein's prediction. The stars near the Sun appeared slightly shifted due to the Sun's gravity bending their light. This was the first major experimental confirmation of general relativity and made Einstein an international sensation. Gravitational waves, ripples in spacetime. Einstein's theory had many other implications. In 1916, he predicted the existence of gravitational waves, ripples in spacetime caused by massive objects accelerating, such as to orbiting black holes or neutron stars. These waves would carry energy across the universe, distorting spacetime as they traveled. For decades, gravitational waves remained a theoretical prediction until the 1970s, when indirect evidence emerged. Scientists observed a pair of neutron stars slowly spiraling toward each other, their orbits decaying exactly as Einstein's equations predicted, due to the emission of gravitational waves. However, it wasn't until 2015, almost 100 years after Einstein's prediction, that scientists directly detected gravitational waves for the first time. The LIGO experiment, a highly sensitive detector in the United States, captured these ripples in spacetime, confirming yet another piece of Einstein's cosmic puzzle. The struggles and triumphs of a genius. Einstein's journey to general relativity wasn't without challenges. In fact, at one point, he became confused about his own equations and believed that a fully general theory of relativity wasn't possible. He temporarily abandoned the idea of finding a complete solution and developed a more limited theory, known as the Endor Theory, in 1913. It took Einstein more than 2 years to realize that his earlier doubts were misplaced. By November 1915, after intense work, he corrected his mistakes and presented the final form of general relativity. This elegant theory, one of the crowning achievements in the history of science, has since become a cornerstone of modern physics, explaining everything from the orbit of planets to the existence of black holes. A new vision of the universe. Einstein's work on relativity shattered the old notions of absolute space and time, replacing them with a dynamic, ever-changing universe where time could stretch, space could bend, and energy and mass were interchangeable. From the bending of starlight to the ripples of gravitational waves, his ideas continue to be confirmed by experiment and observation, reshaping our understanding of the cosmos. More than a century later, Einstein's legacy endures, reminding us that the universe is far more wondrous and mysterious than we could ever have imagined.